Today we're going to talk about geometric sequences. The sequences we have here are obviously not arithmetic because in this one we would add 4, but that's definitely not adding 4. Here we would subtract 5 or add -5, but that's definitely not adding -5. It's hopefully fairly obvious what's happening here, that we're multiplying by 3 and then multiplying by 3 and then multiplying by 3 and then multiplying by 3. Here we're, you could say, dividing by 2 or multiplying by 1/2, multiplying by 1/2, multiplying by 1/2, multiplying by 1/2. So we don't call it a common difference as we do with arithmetic sequences. We call it a common ratio. And we give it the letter R. So in this case, the common ratio is 3, and in this case, the common ratio is 1/2. Okay. Because geometric sequences have strong ties to exponential functions, not all of them, but a lot of them have strong ties to exponential functions, what we're going to see as our functional definition is something that should remind us of the work we did with exponential functions. So in this case, the functional definition says we're multiplying by 3 every single time. So starting from 2, we're multiplying by 3. And for the first term, we didn't multiply by 3 at all, so no times. The second term, we multiplied by 3 once. To get to the third term, we multiplied by 9, or 3 squared. We multiplied by 27 from the first term to this term, so we've multiplied by 3 again. So we express that as n minus 1. For this sequence, starting from 10, we're multiplying by 1/2. And the first term has not been multiplied by 1/2. The second term is the first times 1/2, times 1/2 again, times 1/2 again, times 1/2 again. Again, it is one less time. The second term was multiplied by 1/2 once, like that. Let's try it one more time. So here, for plus 16, that's definitely not plus 16. So it is not an arithmetic sequence. For times 5, times 5, times 5, times 5. So it is geometric. So the common ratio is 5. So the functional definition, starting from 4, we are multiplying by 5. But since the first term hasn't been multiplied by 5, we're multiplying by 5, n minus 1 times. So what happens if what they tell us is the first term and the common ratio? I believe they're going to ask you to find the first 5 terms. I'm also going to ask you to find the functional formula as well. So the first 5 terms, lovely, they gave us the first term. So if my common ratio is 4, I need to multiply this by 4. Then I need to multiply that by 4. Wow, let's get some help for that. 6, and then multiply it by 4. So 24, 96. I'm going to multiply that by 4. 384. Oops. And I'm going to multiply that by 4. 1536. So they get, because they're exponential in nature, they're getting really big really fast. So let's write our functional formula, a sub n, starting from 6. We're multiplying by 4, n minus 1 times. Okay, so let's look at a couple others. So the first term is negative 5. Common ratio of 3, so negative 15, negative 45, negative 135, negative 405. That's stretching my mental math capabilities. Our functional formula, a sub n, start from negative 5, multiply by 3, n minus 1 times. This particular sequence is decreasing, to use some of our vocabulary. It is, so it's monotonic, decreasing. It's bounded at the top by negative 5, but not bounded at the bottom because it just keeps decreasing. Starting at 3, ratio of negative 5, negative 15, positive 75, negative 375. Oh dear. Positive, let's see, 25, 7, 17, 18, 75. Okay, so our functional definition, starting from 3, we've got a common ratio of negative 5, n minus 1 times. To use some vocabulary, this sequence is alternating, so it is not monotonic. It's not bounded above, and it is also not bounded below. Let's try one more. First term is 20. Common ratio negative 0.1. So this would be negative 2, positive 0.2, negative 0.02, positive 0.002. So a sub n, starting from 20, we have a common ratio of negative 0.1 to the n minus 1 power. Okay, again, we're getting alternating. What causes that alternating in a geometric sequence is a common ratio that's negative, because as you multiply it in, a negative multiplied by a negative is going to be positive, and a negative multiplied by a positive is going to be negative. So you can create an alternating sequence. One of the ways to do it is as a geometric sequence with a common ratio that's negative. That's all I have, so give it a try. Actually, I have one more thing I want to show. I am in sequence mode, and I put in one of the sequences we looked at, 10 times 1/2 to the n minus 1. This does say n minus 1 if we look at it. 1/2 to the n minus 1, and I did put the power in a parenthesis. And if we actually look at the graph of this, again, we should see that it is just dots, but that it does look like exponential decay because the base is less than 1. And if I had inserted a negative in here, then what happens to our graph is that it alternates. So it doesn't really look exponential, which is why not every geometric sequence is exponential. The alternating ones can't be considered exponential.